Presenting my Physics 1 Lab 1. So a little introduction. The purpose of this lab is to show the relationship between velocity and time through Newton's laws of motion, specifically Newton's second law. And it is also to demonstrate the differences between a predicted model of a ball and an actual model of a ball with zero velocity and no changes in direction. So, models used. I used a real-life model of a ball rolling across a table. I recorded it and uploaded it to a tracking-based website tracker. I also used an online coded model created through GlowScript. So some fundamental physical principles used. Throughout this lab, we get to see Newton's second law of motion in action. This law explains that an object in motion stays in motion unless acted upon by an external force. And velocity update formula is presented right here on the right. And it basically explains that the final velocity is equal to the initial velocity plus the F net, the force, over mass times the change in time. So this is basically what this lab will go over. Okay. And then systems and surroundings. So the ball is the system, and it's this really nice ball right here. And the surroundings are the table in which the ball rolls across and air resistance, although there's very little air resistance. In some initial conditions, the ball is stagnant, not moving, since there is no force acted on it. And the ball is located at position 0.97 meters at time 0, based on what you'll see in the video. Okay. So, procedures and experiment details. After first pushing a ball across the table and recording the time it takes to cross, I uploaded the video to Tracker. After analyzing the video, I recorded 0.33 second time intervals tracking the ball's location, and you're going to see that in the little recording as well. I looked at the time versus X position measurements and recorded them to form a series in a graph. And then I consulted GlowScript and created my own interactive moving ball simulation. I recorded the measurements and times from GlowScript as well, and I put both position values in a graph and compared my findings. I saw the differences. Okay, so here are the two videos. On the left, we're going to start with that one, is the real-life simulation. Look at that, so beautiful. Okay. And then on the right is what the graph looks like at that same time. And as you can see, these videos were made possible through Tracker. Okay, now on to GlowScript for the coding simulation. As you can see, these are the coding rows I made, and for row 35 specifically, I found the position by taking the X value at 0 seconds when the ball started to move. So as you saw in the video, it started at 0 seconds, and it was at position 0.96. And I found the velocity for row 36 by doing the change in position over the change in time. And on the right, you can see the velocity formula here. So, some observed versus predicted series graph findings. What I found was that both graphs were similar in that they were at the same location and lasted for 2.2 seconds. But I saw, as you can see here, I saw some pretty big differences as well. The predicted position actually has zero velocity, while the observed position was met with friction and external forces, so it was unable to make precisely zero velocity possible. And yes, my graph definitely shows that. So, some possible sources of error from this. There was human error, Possibly. I may have exerted too much force at the beginning when releasing the ball, making the velocity greater than 0 and having more of a net force than 0. And the direction of the ball, although I tried to make it as straight as possible, was tilted at the end of the time, so at the very end there. So what if and what does it mean questions. If the axes were swapped, what would happen? Well, the difference would be that the series would be negative and their slopes would also be negative. And is it possible to determine how many pushes and pulls are on the ball? It's not possible to know how many pushes and pulls are on the ball because of the outside forces such as friction. Thank you for listening.